Hello again, everybody. In today's video, we're going to derive all 4 kinematic equations. And to start us off, we're going to start off with the definition of the acceleration, which is just acceleration is equal to some change in velocity over some change in time. And from calculus, we're going to start with the separation of variables. To start off, we're going to multiply both sides by dt. So we're going to get a times dt is equal to dv. And from here, we're going to integrate both sides. For dt, we are going to start off at some initial time 0 to some final time t. We don't know what t, so we're just going to leave that as a variable. And for the velocity, we are going to start off at some initial velocity, and we're ending at some final velocity. Again, we're going to call that a variable. We don't know what, so it is not a constant, it is a variable. And from here, we just integrate with calculus. On the left-hand side, we're just going to get at evaluated from 0 to t. And on the right side, we're just going to get v evaluated from v0 to v. And from here, we're just going to simplify a little bit. This is just at is equal to v minus v0. And if we just rearrange this a little bit to make it more useful later on, we're just going to get v equals v0 plus at. And there you go. There is our very first kinematic equation. And from here, we're going to redo another separations variable with calculus. So to start us off, we're going to start with the definition of the velocity this time. So velocity is just equal to some change in position over some change in time, and that's equal to the result that we just got before this, v0 plus at. And once again, we're going to do another separation of variables, so multiply both sides by dt. That leaves us with dx plus, in parentheses, v0 plus at times dt. And we are going to integrate both sides, starting with the position at some initial position to some final position. And with time, starting at some time 0 to some unknown time again, t. So we're just going to evaluate x from some initial position to some final position. And the right hand side, v0 t plus at squared, and then divide that. Both of these are from 0 to t. And to conclude everything here, the final position minus the initial position, v0 t plus 1/2 at squared. And to make the left side a little bit more convenient for later on, we're just going to simplify this to delta x. That's just to signify some difference in position. And ta-da! We have our very second kinematic equation. And from here on out, we're going to start using algebra to derive the other missing 2 kinematic equations. So let's begin on that. So here I just have both kinematic equations that we just derived, and let's make the left-hand side a little bit more useful. We're going to make this at equals v minus v0. And just to point this out a little bit more clear, we're going to use the right side, because this is in fact 1/2 a times t, that's in parentheses, times another t. And we can just plug in the left-hand side into this at, so let's begin on that. We're going to have delta x is equal to v0 t plus 1/2, and remember we're plugging in that term, so it's v minus v0, and then there's a t term out there, and I'm going to factor out a t and plug in the 2, so this is t in big parentheses, v0 plus v minus v0, all of that over 2. And here I can just sneakily multiply a 2 over 2, which is basically multiplying by 1, just to combine all of these terms together. That'll get me t, in parentheses again, 2v naught plus v minus v naught, and all of that is over 2. And from here, just to finish things off, we just combine terms again. That is equal to t multiplied by v plus v naught over 2, and that is equal to delta x. And here we go. Here's equation number 3. Let's move on to number 4. Alright, I have rewritten both of the derived equations once again. And one more time, in order to solve for the last kinematic equation, we have to make this left-hand side equation a little bit more useful once again. This time we solve for t, which is just v minus v naught all over a. And then here we can we can substitute t for the equation on the right side. So let's begin that. And the algebra is about to get a little bit heavy. So delta x equals v naught, and then we plug in for t, remember, v minus v naught over a. That is plus 1/2 a, and then plug in for t again, v minus v naught squared, all of that stuff, over a. And now we have to do a little bit of algebra for this one. Multiply the v naught, v naught minus v naught squared, all of that over a, plus 1/2. I'm going to preemptively multiply the a inside. That's going to be v squared minus 2v naught plus v naught squared. All of that stuff is over a. And then here, in order to combine everything that we have had so far, once again I'm going to sneakily multiply a 2 over 2, so that we have 2v naught minus 2v naught squared plus v squared minus 2v naught plus v naught squared, and all of that is over 2a. Alright, let's just observe what we have so far, so we can combine like terms. This stuff can be combined with this, just to cancel that out, so we never have to worry about that ever again. And then, let's see what else. This minus 2v naught squared can be combined with this plus v naught squared. And then we have to combine everything all over again. I told you the algebra would be kind of dirty. Alright, let's continue. Once we combine everything all together, we're going to get v squared minus v naught squared over 2a. And remember, this was equal to delta x at the very beginning. And I would just multiply 2a on both sides, and we finally have our fourth kinematic equation. 2ax is equal to v squared minus v naught. And we're finished! V naught squared. And we're finished! Hopefully this video helped you guys out with trying to start with calculus with the definition of the acceleration for the first two kinematic equations, and from there we have to do a whole bunch of algebra to derive the last two kinematic equations. And you are now ready to use these kinematic equations for problems of motion.